Okay, welcome to this next video for Chem 161, looking at Chapter 4 materials, where we'll touch on some additional tools that we have for handling Lewis structures, specifically the idea of checking options with a formal charge calculation. Okay. So let's start with that idea. So we have the concept of a formal charge, sometimes abbreviated FC. It's a hypothetical charge on a bonded atom that tells us whether the atom has any missing or any extra electrons. Okay, so that idea kind of follows with the equation below. So the first piece here of the formal charge calculation is an estimate for the number of electrons an element should have. Okay, we get that by simply stating the number of valence electrons. Okay, and then this represents what you would have for a neutral atom if we did a Lewis dot structure. So as we've seen before, for example, oxygen in its Lewis dot structure for an isolated oxygen atom, there's no charge on this structure, and so we can see that this has the number of electrons it should have. So that idea is built into that first sort of term of this equation. The next two help us count the number of electrons that an element does have when it's bonded, when it's in a molecule. Okay, so the middle term here is half of the electrons that are in bonds. Okay, so because we have sharing there, we can only count half of them. All right, and the last term here is the number of lone electrons. Okay, so if we have a lone pair, we are going to count both of those as a value of 2 in that case. Okay, so lone pairs are fully assigned to the atom. There's no sharing, so that makes sense as well. Okay, so we can use this because occasionally we will make a mistake with Lewis structures, or we'll have options when we borrow pairs, and we can rationalize which structure is the best one based on assigning the lowest formal charge to centers in a molecule. Okay, so that is, when we have structures that have the same lowest formal charge, we'll use the one that has negative formal charge on the most electronegative element. That's an idea that drops out of that. And we would also show that if we have options, we would never want formal charges that are the same sign next to each other. We wouldn't want to put two positive formal charges next to each other. That would be electrostatic repulsion. Okay, so that final bullet there of having adjacent atom in a structure should have different signs on their formal charge value. So as we saw earlier, we had to negotiate COCl2 from a starting point where we had something like this, and we had 6 electrons surrounding each of these periphery atoms. Okay, and we saw that the octet in the carbon was not complete, and so we had to negotiate which element are we going to borrow from. Okay, so in doing this, we showed in a previous video that borrowing from the oxygen was correct. If we had chosen other options, we could have had something like what we have in option B, where we have a double bonded chlorine instead of the double bonded oxygen that we have. Okay, so we eventually said that the correct answer was A, as we sort of borrow a pair of electrons from the oxygen. Okay, so let's use our formal charge here to rationalize why that was the right choice, why A is the right choice. So let's look at the oxygen atom and calculate the formal charge here. So I'll put a little FC, and we'll see that the oxygen atom comes from column 6, so it should have 6 valence electrons. We're now going to subtract half of the electrons that we see in bonds. There are 4 electrons in the double bond, so half of 4. And then we're going to subtract the total number of electrons in lone pairs. 2 lone pairs, total of 4. So this is going to be minus 4. 6 minus 2 minus 4, this is a formal charge of 0 for that oxygen center. Okay, you can do it for all the other atom centers. So the formal charge here is going to equal, carbon is in the fourth column, 4 minus a half of. Now there's a lot of electrons in bonds near that. That's minus 8. And there's no lone pairs on that carbon. So that's 4 minus 4. That's a formal charge of 0 as well. These two chlorines are identical if you think about the bonding circumstance and the number of lone pairs. So by doing one calculation, we do them both. The formal charge on both of those centers is going to be 7, chlorines in the 7th column, 7 valence electrons, minus half of those that are in the bonding circumstance, so 2 electrons on the single bond, and now minus the number of lone pair electrons, so a total of 6 there. 7 minus 1 minus 6, that's 0. Every center here has a formal charge of 0 for this option A, okay? When we do other options, you'll see here that this formal charge ends up as formal charge equals minus 1. You'll see that this, again, looks like a previous chlorine that we've looked at. That's formal charge equals 0. When we do this one, we'll do this one with a full calculation here. Formal charge is equal to 7 minus a half of the number of electrons in bonds, so half of 4. And then minus the number of lone pairs, so minus 4 for the 2 lone pairs that are there. So that's 7 minus 2 minus 4. That gives us a positive 1 value. And our chlorine here is formal charge of 0. So here we've put a minus 1 on the electronegative oxygen. That's okay. It's a value greater than 0. Not ideal, but we could accept a minus 1 occasionally. This is where the red flags are raised. We have a chlorine, a very electronegative element, direct neighbor to the most electronegative element in the periodic table, fluorine. That's a value of plus 1 formal charge on that fluorine. We should not have positive formal charges on very electronegative elements. That's a red flag. So this is why we would rule out option B for that structure. So it was option A with the double bonded oxygen that was correct. And so it was correct to borrow a lone pair from the oxygen and not the chlorines to complete the octet on the chlorine, on the carbon, on the central carbon. So that is how we can use formal charge to help us there. Okay, so some other options as well that I'll just highlight here. If you had started with the wrong skeleton, again, you could see that can be rationalized to be the wrong structure by a formal charge calculation. Okay, so you could invite you to kind of look at the formal charges here. In short, you should be able to rationalize that our formal charges on these chlorines are 0 and 0. Okay, that's what we would want. We can look at the formal charge on this oxygen, Fc, 6 minus a half of all the electrons in bonds. I see 8 there, minus 0 for the number of lone pairs. This formal charge here is 6 minus 4. This is plus 2. Huge red flag. A plus 2 formal charge on a very electronegative element, oxygen, neighbor to the most electronegative element in the periodic table, fluorine. Huge red flag. That's not good. You can do the formal charge on this chlorine or carbon. That carbon is formal charge 4 minus half of the electrons in bonds, so minus a half of the 4, and then minus the 4 that reside in lone pairs. 4 minus 2 minus 4, that's going to be a formal charge of minus 2. Very high value. If we can avoid going to minus 2 on any formal charge center or avoid going to positive 2 on any formal charge center, that would be good. So a lot of red flags on this option. Formal charges helped us rule out option C here, where we would have put the wrong atom at the central feature of the skeleton. Clearly a wrong option. Okay, so further justification for our first answer, A being the correct one. Okay, so again, very useful to use your Rule 7 from your previous rules to help us rationalize the formal charge of options that drop out of our Lewis structure kind of rule set for developing those options. So let's take a look at another example. So we'll look at CO2. Okay, so as you recall, we have to take stock of the total number of valence electrons here. So we are going to get 6 valence electrons from each oxygen. We are going to get 4 from the carbon. So that's a total of 16 valence electrons to work with on the Lewis structure. So for this molecule, we'll put carbon in the middle. We can put an oxygen and an oxygen. By building this skeleton, we've just used 4 electrons, so minus 4. We now have 12 left. Electrons to the periphery, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We've now used all valence electrons. So all the electrons we need in the Lewis structure are there, but we need to consider octets. Oxygen and oxygen each have an octet. Carbon is missing 4 electrons. So we will consider an option where we borrow a lone pair to do that. So the outcome here, borrowing a lone pair, would be oxygen atop, still bonded singly, carbon below now bonded twofold to the oxygen, and we've got now 2 lone pairs in that oxygen instead. This is a step in the right direction. We've got carbon now with 6 electrons closer to the octet, and we can even use the formal charge here as a way to track what we've got. If you look at the formal charge here, you will find that the formal charge is equal to -1 here. So please stop the video and confirm that that's what we have for formal charge. If you look at the formal charge here, you'll find that the formal charge is 0. 0 for that option. And we'll do this central carbon more slowly for the purposes of exercising that idea. So formal charge 4 minus half of the electrons in bonds, so that's minus half of 6. No lone pairs, so it stops there. 4 minus 3, that's a formal charge of +1. Not as good as we might be able to do, so we'll look for options where we can get this formal charge on the carbon even lower. Towards 0 would be ideal. Okay, so let's take a look and see what else we can do. Well, just like we saw earlier, if an octet is incomplete at a central atom, let's borrow a pair of electrons. We saw that this formal charge was at 0 a moment ago, so we should not borrow more from that same oxygen. We saw that this formal charge over here was -1. The result of borrowing a pair is to bring less formal charge negative to that site. So by borrowing a pair, we go from -1 to 0 on that top oxygen. When we do this, the formal charge of that top oxygen will be more acceptable, and the carbon sees an extra pair of electrons. Octet is complete, and you'll see that the formal charges work out. So after this, we end up with double bonded oxygen as such, and another double bonded oxygen as such. And we now have an octet at that central carbon, as well as at each oxygen. Formal charges all around are 0. Okay, so this carbon had a red flag before. We'll just show that one. And I invite you to do the formal charges on the other 2 oxygens. Here we have 4 minus half of all the electrons in bonds, so that's half of 8. No lone pairs, so 4 minus 4, that is 0, as are the other formal charges. Formal charges of 0 all the way around. This is now the complete and fully rationalized Lewis structure for CO2. Okay, 2 double bonds that resulted from borrowing of lone pairs from the outer atoms in the Lewis structure. Okay, let's do one more here. So let's just make some room for that. And we'll look at Hcn Hydrogen Cyanide. This is the dangerous chemical that is poisonous, and we need to be careful handling any type of cyanide compounds. So Hcn. Okay, so we've got hydrogen gives us 1 valence electron, carbon is going to give us 4 valence electrons, and nitrogen is going to give us 5 valence electrons. So we have a total of 10 valence electrons for a Lewis structure. Carbon in the middle, and we're going to populate the rest, so nitrogen and hydrogen. Okay, so put them kind of flanking. The top position and the bottom position are empty, that's fine. I've just used 4 electrons to build my skeleton, so I now have 6 valence electrons left. And we start by populating the outer atoms now. Hydrogen only wants a duet. It has a duet by the borrowed pair right at left. So we'll now put 1, 2, 3, 4, 5, 6. We've just used 6. Establish an octet out nitrogen, none left. Our skeleton has all the valence electrons that we are allowed to use, and we now need to consider octets on the central carbon. So clearly we only see 4 electrons on that carbon. We need more bonds on that carbon to help us. So we can consider an option where we borrow a pair of electrons. This structure would evolve to a version that looks like this. 2-fold bonding from the nitrogen to the carbon. Only 2 lone pairs of electrons at that nitrogen now. And we can check our formal charges. At this point, the formal charge of nitrogen was 5 minus half of all the electrons in bonds. I see 4 there. And now minus an additional 4 for those lone pair electrons. 5 minus 2 is 3. 3 minus 4, that puts a formal charge value of -1 at that site. Formal charge on the carbon here is going to be 4 minus 3. That's going to be a +1 result there. Better than where we were before borrowing, but we need to try to find formal charges of 0. So let's keep going. We still need an octet on that carbon. The only place we can borrow electrons is from that nitrogen again. So we'll borrow yet another pair of electrons from the same nitrogen, trying to achieve an octet. In doing so, the structure evolves to the following. Carbon with a triple bond to the nitrogen, and we've left 1 final lone pair on that nitrogen, and we still have our duet hydrogen at left. Looking at that now, you can see we have an octet at that carbon, and we've got nitrogen also with an octet at right. And thankfully our duet of hydrogen is untouched. Okay, we can do a quick formal charge here. So now this will be nitrogen is 5 minus half of the 6, so 5 minus 3 is 2, and then minus the 2 for the lone pair, that's a formal charge of 0 right there. Carbon, 4 minus half of the 8, that's a formal charge of 0. And then we can even do the formal charge on the hydrogen. Formal charge of hydrogen is going to equal 1 minus half of 2, and that is going to give us a formal charge of 0. We've got formal charges at each atom center. This is the best option. Our final Lewis structure is this one, rationalized both by octets as well as formal charge checks. Okay, so that is how we apply the formal charge idea to rationalize any charges within centers in a molecule, and to choose between options of Lewis structures as we go and as we consider potential errors or negotiating between borrowed centers out on the periphery of a Lewis